ray, and I'm going to call this theta 1, and I'm going to call this theta 2. Okay? So theta 2, well, what does Snell's law say? Snell's law says, I'll draw it up here. Oh, brother. That dog. Snell's law says that the index of refraction what we have with the air, let me say this. The air has an index of refraction of 1. Okay, glass typically has an index of refraction of 1.33. Now we haven't even defined what this is yet, but we will. Okay, we will. But before we get there, the Snell's law says that the index of refraction N1 times the sine of theta 1 is equal to N2 times the sine of theta 2. Okay? That dog. Excuse me for a second while I get something from my dog. I'll be right back. Sorry, my dog was chewing a pad for a knee pad for playing hockey and soccer. So, okay, where were we? Okay, Snell's law. Snell's law says that the index of refraction times the sine of this angle 1 for air is equal to the index of refraction for glass times the sine of theta 2. Okay, now what is the index of refraction? I'm going to come down here and say, okay, light travels with the speed of c, which is 3 times 10 to the 8th meters per second. Okay, that is the speed of light, 3 times 10 to the 8th meters per second, which is also roughly about 186,000 miles per second. Okay. Now that's that's rightfully that is the speed of light in a vacuum. Okay, and for practical purposes, that's also the speed of light in. I see where he. I'll be right back. The dog is into something else. Sorry, I'm back. Need to teach that dog. Actually, we need to. He's just a puppy. That's the problem. Okay. This is also the speed of light practically in air. Okay, but if this is air, if this is glass, what happens, or media like glass, the speed of light here, the speed of light slows down, and the speed of light in glass is not equal to c. The speed of light in glass would be equal to the speed of light divided by n, and n is what we call the index of refraction. Okay, for glass, roughly the index of refraction is about 1.33, depends on the type of glass, but for your common everyday glass like for windows, it's about 1.33. So we have 3 times 10 to the 8th divided by 1.33. So this, if I take my calculator, 3 divided by 1.33, I get about, did I do that right? 2.26 times 10 to the 8th meters per second. Okay, so the speed of light actually slows down when it's traveling through the glass. Okay, but roughly 2.26 times 10 to the 8th meters per second. Now you may think, well, what's the big deal? I mean, this is super, super fast. This is still super, super fast. You know, why do I care? Well, this property of the speed of light slowing down makes a dramatic effect. If the speed of light did not slow down, we would not have a refracted ray, lenses wouldn't work, optics wouldn't work. This is what's responsible for the bending of light in all kinds of media. Okay, so the good Lord set it up such that that the speed of light naturally will slow down in denser material. Okay, so now in the way that we describe the way we describe it, and this was actually described multiple hundreds of years ago. If you look on page 401, okay, there's a picture, and it's a very, very good picture on page 401, and this picture goes back probably hundreds of years when even people like Isaac Newton were doing this. Initially, okay, we've talked about the idea of light rays being particles, or light rays. We even talk about it as a light ray, but actually we also have wave phenomena. We know that initially people thought light would travel in waves, and there's good evidence. Remember, there's a particle. Have we talked about this? Yes, we have. I think the particle wave duality of light. We've talked about this. The idea that in some cases light travels as if it's a beam of light, it's a ray of light, like a particle. In other cases, light behaves as if it's traveling in waves. So initially, even going back to Isaac Newton, people like that, they talked about this. They talked about, is it a light or is it a wave? And they had good evidence for actually both, just like we do today. We have good evidence for both. If the picture on page 401, if you think about it in terms of rays, or waves, light waves, that is, okay, if the ray is traveling this way, then actually we can talk about light waves. And these lines will represent, imagine a ocean wave where you have the highs and lows and highs and lows. These lines will represent the highs, and then there's a low in the middle, and then the high, and then a low in the middle. So lines represent like the peaks of the wave. Okay, the peaks of the wave. Okay, so if the wave is traveling this way, then the waves are perpendicular to that. Okay, just like an ocean wave. If the ocean wave is traveling this way, the wave peaks are lined up perpendicular. Wave, a wave, and a wave back behind it. Okay, so the wave is perpendicular to the direction it travels. Okay, this being a transverse wave. Okay, so now if this is air and this is glass? Now this is denser. The glass is denser. So what happens when this light wave gets to here, it's a more dense material. It just naturally wants to slow up. It slows up. So it slows up. How does it slow up? Well, it can't travel as fast when it gets to here, it can't travel as fast, so it has to slow up. So it slows up, so this starts to bend. Okay, the next wave coming in here, whoops, let me come a little. Again, it will bend. Okay, it will bend because the wave actually physically travels slower. So you start to get this natural bend here. Okay, there's a bend, and what happens is here, so the wave comes in, but it's bent this way. You would think it would go this way in glass, but it naturally wants to bend inward into the material because it's traveling slower. In glass, the light wave is traveling slower. So there has to be a natural bend in order for there to be a continuum wave. Okay, a continuum of the wave from the dense material into the not so dense material. Okay, so that's kind of a physical description of what's going on as to why there's a bending in the glass of the light ray. Now remember, when the light ray comes in, it bends into the glass toward the normal. So this theta 2 angle to the normal is less than theta 1. Okay? So if this is, as an example, suppose this is 40 degrees, this angle here would be something less than that. It may only be 35 degrees. Okay? It all depends on the ratio of theta 1 and theta 2, N1 and N2. Let's do an example. Okay, let's suppose that theta 1 is 40 degrees. Okay, let's solve for theta 2. Okay. N1 is 1. That's the index of refraction for air. N2, let's use glass, typical common glass, index of refraction for glass. Okay, let's use Snell's law to solve for it. Well, let's solve for theta 2. N1 times sine of theta 1 divided by N2 equals sine of theta 2. Okay, let's plug some numbers in. N1 is 1. This is sine of 40 degrees divided by 1.33 equals, okay, this is where you take your calculator. When you use your calculator, make sure your angles are in, most calculators can flip between degrees and radians. Remember, sometimes we want to use radians, but other times, like this, we want to use degrees. So make sure we're in the degree mode. So type in my calculator, type in 40, and then I do the sine of that, and divide by 1.33, and I get 0.48329. And I'm not going to round off at this point, because then I'm going to take the, remember, that's equal to the sine of theta 2. Now theta 2 then is this what we call the inverse sine or arc sine of 0.48329. Some calculators say it's the inverse sine. Sometimes they say it's the arc sine. It's actually the same thing. It would be, in other words, it's the angle whose sine is 0.48329. So with that number right in your calculator, I just simply push arc sine, and I get theta 2 is equal to 28.9 degrees. Okay? So for air, if this is air with and this is glass with the index of refraction of 1.33, if this is 40 degrees, this angle here would be smaller, 28.9 degrees. So you see, it's definitely bending into the normal. This is a normal line. Okay. So one of the properties of the Snell's law, if you go in from an index that's small to an index that's large, you bend into the normal. Okay. Now, let's talk a little bit about, I need to talk about this. The book doesn't really talk about this, but if this were a higher level physics class, higher level optics class, we'd talk a lot about this. That's intensity, okay? You may think of this, say this is 100% of the light beam coming in, of the instant light. You may ask the question, well, how much light gets reflected and how much light gets refracted? Because both are happening. And indeed they are. So, but the book doesn't really talk about that. Well, why doesn't it talk about that? Well, it's a difficult topic. I shouldn't say it's difficult. In order to figure out how much intensity, how much energy is going into the reflected beam versus a reflected beam, we have to talk about polarization. Because what happens is, whenever you have a surface like this, the light light reflects and refracts differently based on the polarization. We're not going to talk about that at all. Polarization, and you think of polarized glass, sunglasses. If you have a polarization deals with the electric light field in the light beam itself, and it's either polarized one way or it's polarized another way. And but in order to deal with this, we have to talk about that, but that's way beyond our subject here. So instead, what I'm going to do is I'm going to give you a rule of thumb. And the rule of thumb is pretty good. The rule of thumb says this, is that when you're going from air into glass, this rule of thumb only works going from air into glass. The rule of thumb says that your reflected ray is about 4%. And your refracted ray is about 96%, okay, of the intensity. So what you can see from this is that most of the energy coming in is refracted. Only a little bit, about 4%, gets reflected, okay. This explains why you can look through a glass window, okay. When you look through a glass window, suppose this is a thin piece of glass, and there's air on this side, okay, if 99% of, if say 96% was reflected, we would never see, we'd only see a little bit through the glass. But fortunately, the majority of the ray does get refracted, and then it gets refracted again. If this were air, it would come out like this again. So you actually can see right through the glass with only about 98 or so percent transmittance through the glass. Actually going to have some more reflection right here, but that's further complicated. But this also explains why when you look in a plain sheet of glass, like through your glass window, you can also see a faint reflection of what's behind you, of what's over inside the room. That's because you can, there is a little bit of reflected 4% energy coming in. Okay, so a sheet of glass, you can mainly see through it, but you can see a little bit of reflected light, just a little bit. It's only about 4%. So hope that explains things a little bit. And let me also, since we're on the subject, I know this is very busy right here, but I'm going to come over here and talk about something a little bit more. And again, if this were a full class on optics, we would spend a lot of time on the whole subject of dispersion. Really, all of what we're talking about here comes under the optics heading of what's called dispersion. Dispersion. The idea of dispersion, this is true for a piece of glass or anything, or any kind of optic material is that the speed of light, you remember the wavelength, light has a certain wavelength. For instance, if the wavelength is for visible light, if wavelength is of the order of say 700 nanometers, it's in the red region. If the light wavelength is of the order of like 500 nanometers, we're in the blue region. Blue region. Okay, so it turns out that the index of refraction is a function of the wavelength. Okay, and this is really what we mean by dispersion, and this causes all kinds of optical effects. Actually, in some cases, optical effects you don't want to happen in your lenses, but in other cases, beautiful optic effects like the rainbow. Okay, the rainbow is the idea of the rainbow is you have this like a prism. Okay, if I have, and again, this is not covered in the book, but if I have white light, remember white light has all the colors of the rainbow in it. The light comes in, it reflects, it refracts, but it does so, it turns out that the index of refraction varies with the wavelength. So what that means is the amount of bending, the dispersion, the amount of the bending depends on the wavelength. And so what you get out is the whole rainbow, red to blue. Actually, it'll be the other way around. Blue is bent higher, red is bent not as much. Okay, so and of course this goes all the way back to people like Isaac Newton who did experiments with this. But this would be the prism effect. The whole prism effect and the rainbow effect is brought about because of what we call dispersion. The idea that the index of refraction changes with the color, the wavelength. For each color, there's a slightly different angle at which it bends, so the colors separate out into the rainbow. Okay, so dispersion can be a wonderful thing. It brings about all kinds of wonderful effects, and we get spectrometers because of that, and we get rainbows because of that. But it's also, think of your camera, it's also a negative effect when you can have things like chromatic aberration. Chromatic aberration of your lenses is caused by, unfortunately, this is a wonderful effect, but when it comes to lenses and cameras, it's not so good because sometimes the chromatic aberration effect is the idea that the lens doesn't focus right for every color. It focuses better, that is, the focal point shifts a little bit depending on what the color is. Okay, so it can bring about some problems with lenses and cameras and things like that. But it's all kind of covered under the realms, the physics of dispersion. But we can't talk any more about it than that. So let us go on to page 405. This is an interesting subject, and we could talk, we could spend all day talking about this, but we just don't have the time. That's why, if you're like me, you'll take lots of optics classes. Okay. And I should also add that it can get quite mathematical, too. Okay, page 405, we're going to start talking about lenses. Remember before we talked about mirrors, where we were simply reflecting off the mirrors. But now that we have Snell's law, we understand a little bit more Snell's law, we can understand more the concept of the lens, the idea that the beam of light in the lens, look on page 405 and 406, especially 406. Again, when you have a lens, lenses come in general two varieties. We have what's called a convex lens, and a convex lens would be where the optic axis, where it looks like this, it's bigger in the middle and smaller to sides, versus a concave lens where it's thinner in the middle and bigger on the sides. Okay, just like if I were doing a convex mirror looking from left to the right, convex mirror looks like this, and a concave mirror looks like this. The convex lens has that shape on both sides. The concave lens has that shape on both sides, this kind of curving in shape. Okay, so that's the convex and concave lenses. So we're going to look at both of them. And this is, I think, really the last. We're going to do some more ray diagrams on convex and concave mirrors, and really that pretty much wraps up the chapter. We'd like to stuff more in, but we just don't have time. Okay, again, you draw your optic axis, and let's first start with convex. And I'm going to draw a big, fat, convex lens. Okay. Now, I didn't exactly draw the optic axis right in the middle, did I? Okay. Now, if we have a parallel in ray. Okay, now, when you get to the glass, remember this is air and this is glass. We have to apply Snell's law right at that surface. Do you remember Snell's law? Snell's law, N1 times the sine of the theta 1, this is the air side, equals N2 sine of theta 2. This is the glass side. Okay, air side, glass side. Okay, well, we really have to apply Snell's law right at this surface. We have to draw that would be the normal, and it's rather tedious. We're not really going to do this for real, but I'm just going to show you how you could do it. Okay, so the light ray bends, here's theta 1, little theta 1, and here's theta 2, and the light ray, notice how the light ray bends in. Light ray bends in, so it's coming parallel in, but then it dips down. Okay, now I get to another surface. Okay, I get to another surface. Okay, here's the incoming ray, and now the outgoing ray, remember, it's actually going to bend out even more, because you remember, this ray, this angle is larger than this angle, and this angle must be smaller than this angle, so it's actually even going to bend even more. Whoops. That is, this angle must be greater than that angle, because this is air and this is glass. Okay, so what happens, the ray gets bent 2 times. It's bent here and then it's bent again, and it comes right down here, and this point right here is what we call the focal point. And so all incoming parallel rays get bent, and they get bent right into the focal point. Doesn't matter where you are, all the incoming rays get bent right into the focal point. Even a ray right along here just goes straight through. So all the rays coming in get bent. So the focal point is exactly that. The length would be from here. The focal length is from the center of the lens to that focal point. So that would be, the focal length is that distance right here. Okay? So from that in mind, Now we start solving some problems. Okay, one more point. Forgot about that. Suppose this were a concave. That's okay, this is convex. What about concave? A concave lens in a concave lens, okay, the parallel rays that we have a focal point. Actually, there's a focal point on both sides of the lens. Lenses can be used frontwards or backwards, of course. So there's a focal point on both sides, just like there's on the concave lens, there's a focal point on both sides. What happens here is a parallel ray coming in. Again, we apply Snell's law here, but the surface is bending the other way, so we apply Snell's law. This time it bends upwards, and we apply it one more time, and it has to bend upwards even more. Okay, so the ray comes in and bends up this time because the surface is